speaker, Shravan Hanasoge from AFR Mumbai. So he will talk about the equatorial confinement of turbulence in the sun, his latest result using normal mode analysis, I guess, from simulations too. Over to Shravan. Yeah, go ahead, Shravan.
Thanks a lot, Rajguru, and thanks to the SOC for inviting me to give this talk. I really enjoyed many of the talks in this conference, so thank you for organizing it. So for many of you who've heard this talk maybe a couple of weeks ago at ASI, I apologize. This is quite similar to that talk as well. This is about a recent result that we came up with, which is namely the confinement of turbulence, large-scale toroidal flows close to the equator. So differential rotation, we all know, many of us know, is a very important feature and is thought to drive the solar dynamo. However, it's a major unsolved question as to what drives it and the governing mechanisms, for instance. Numerical simulations, which are on the right here, don't do a very good job of predicting differential rotation, and so it's a constant question as to what mechanisms might be propping this particular rotational shear. And recent results, including with other spectroscopy and a variety of other measurement techniques. This one is for the one that I'm showing here. It's from astroseismology, but suggests that there's quite a few stars, sun-like stars, that also have solar-like differential rotation. They have a much sharper differential rotation, so it's nearly 50% of the nominal rotation rate. But nevertheless, these are all fast-rotating equators, just like the sun. And so it certainly suggests that this type of latitudinal shear, rotational shear, has some sense of maybe universality or some important underlying mechanism connects all sun-like stars. And so it's very important to try to understand what might be driving these. And so the solar convection, which is long thought to be the primary mechanism, is a fair amount that's known, but a fair amount that's not known. We know that we think, at least, that long-range velocity correlations are central to this angular momentum balance. But convection on large scales is a bit of a controversial topic, and it's especially in the interior, it's difficult to measure. And there have been many attempts at detecting large scales of convection, but with generally lack of success. And particularly, what's interesting is as Srini was describing a little while earlier, the depletion of power at large scales. And this I want to draw your attention to. This is the most interesting because it contradicts what we think, and numerical simulations appear to suggest it should be the behavior of convection in the sun. So we ask ourselves, do we not understand convection? And there's a plot here which shows various constraints. Here is power, some type of velocity amplitude. Horizontal axis is harmonic degree. And we see seismology, which is a result in 2012. It's since been revised. I'm just showing this old measurement here. And numerical simulations, which there's a big gap. There's another actually more significant issue that we didn't catch in that previous paper, which I'll describe later in this talk. And there's a variety of other constraints that show significant departure from large-scale global numerical simulations. So this work is a seismic work. I'm not attempting specifically to try to prove or disprove a calculation or a methodology. We just wanted to go and try to understand what was happening in the sun. So the primary way by which we decompose the velocity field is this very clean Chandrasekhar-Kendall decomposition, where you decompose the velocity, generalized 3-vector velocity field in a sphere in terms of radial and poloidal, or I guess these two are kind of connected. They're connected at least by the momentum, by the mass conservation equation. And this is the toroidal flux. By construction, toroidal flow, sorry. By construction, the toroidal flow does not have radial components. As you can see, it's perpendicular to so it's tangential, it's on the sphere. And it's also divergence free. So it's not like a poloidal flow, which is heat carrying, right? So poloidal flows tend to sort of climb up, they move out, so like for instance in a supergranule, and they fall back in. So that's an instance of a colloidal flow, which, or even granulation, which we know carries thermal flux. But these are incapable of carrying thermal flux. But they're nevertheless a significant component, as I'll show you, of the convective flow spectrum in the sun. Okay, so as I said, we focus on toroidal flows. There's a specific reason we did this. These are relatively easy to measure in this somewhat novel application of this method called normal mode coupling, which I will also describe. So this was the easiest thing to measure, and among the other types of measurements that you could make using that technique, this is the cleanest. So here are the two things that I show here. There's a third one, is temporal frequency as well. But the two, power is a function of temporal frequency, but I won't really be describing that. I just want to describe the power spectrum as a function of wave number. S is harmonic degree, and that's simply the sum over T is the azimuthal order, sigma is the temporal frequency. And the other thing, which is a type of shape of the types of modes and where on the sphere these modes are sitting. So S minus mod T gives you some information about this. And that's just, you basically sum this at constant values of S minus mod T. So these two power spectra are very important constraints on the type of convection that persists in the sun. So why are toroidal flows important? As I said earlier, toroidal flows are not carrying thermal flux. So, I mean, are they even relevant? And the answer is yes. These are surface measurements from a model that Hathaway developed. The black line is the total velocity of convection that he measures at the surface, harmonic degree, velocity, amplitude. Blue is toroidal flows, and red is poloidal flows. So you see up to 100 or so. These are not irrelevant. They're fairly important. This is about a factor of 2 or 3 off. But certainly when you go to 20, 30, 40, by up to about L of 40 or so, they're really right on. In fact, toroidal flows even dominated low L. So they're quite important in the dynamics, at least on these scales. And numerical simulations. This is from Hideyuki Hotta, who shows this is the dashed toroidal flow power, RMS velocity versus radius. Apologies, versus radius. This is poloidal flow power, and you can see the two are essentially right on top of each other. So they are important in some sense for the dynamics, and we don't really know because people don't really talk about the decomposition of convective flow power. They just say this is the total velocity amplitude. So it's important to try to characterize it this way and understand the underlying physics. There's a paper here for Horn and Shishkina who suggests that this ratio of toroidal to poloidal flow power even indicates the type of convective regime in which the sun or the system lies. So, we use seismology for reasons that I don't really need to describe here to make these measurements. And so I'll tell you a little bit about this technique. It's a very nice technique. So here's a little video of MDI oscillations, oscillations measured using MDI. And you can see supergranular flows in the background. That's this scale that you see. And the static in the center, these stochastic waves excited by near surface turbulence. As many of you know, these waves form resonances. They propagate within the interior. They totally internally refract and then re-emerge to the surface, forming resonances. And at the surface, we measure the surface line of sight Doppler velocity is a function of space and time, theta, phi, and t, which we then transform into spherical harmonic space LM and omega. Note that I use ST for the flows, the flow wave number, harmonic degree, and azimuthal order. LM I use for the modes. Okay, omega is the frequency, so we transform it into both time and spherical harmonic domain. Okay, so what is the method? A very, very elegant method. First introduced in 1989 by Martin Woodard in helioseismology. And the idea is you come up with a simple reference model, sufficiently close to the sun, but doesn't need to be overly complicated, and a model that's non-rotating, non-convecting, so on and so forth. For instance, model S. And the sun, of course, is a departure from this reference model, has all of these features. And the reference model has a set of eigenfunctions. And because we are operating luckily in the regime of linear waves, these eigenfunctions form a complete and orthonormal basis. And you can express any other function on the sphere in this basis of eigenfunctions. So it turns out to be very productive because the sun has a different set of eigenfunctions, of course, than the reference model. but you can cleanly write every eigenfunction of the sun as a linear combination of the reference eigenfunctions, like so. And this alpha kk prime are coupling constants. And these coupling coefficients, this is a standard quantum mechanical recipe, and it's been around for nearly a century, very widely used in geophysics, although the particular application to helioseismology is unique. And a lot of this development, of course, is to be credited to Martin Woodard. So it turns out that this is the central measurement that we make, which is the line of sight Doppler velocity correlated at two frequency channels, omega and omega plus sigma. The distance between this sigma tells you about the inverse time scale of the flow that you're interested in. And here, note that L, I use the same harmonic degree. In general, you can broaden it and use L and L prime as well, and it expands your set of measurements dramatically. And there's a huge amount of information that we still need to exploit, and that's anyway part of future work. But for the simplest case, as I said, that we pursued here, L and L the same, and the distance M and M plus T, the T tells you about the azimuthal order of the perturbation, in this case, the flow. So turns out that those coupling coefficients that I told you about is connected, this is a mathematical weight function to some weighted sum of this correlation product. And so we have a lot of data that we can look at. And ultimately, through some tedious algebra, you can write these measurements, which is this phi star, some combination of those phi stars, as this integral times toroidal flow, which is an unknown quantity. These coefficients are exactly what we want. And these are some functions, the mathematical functions that you can derive. It's a very beautiful method. We're increasingly starting to apply it to lots and lots of things. We've verified that the method works in differential rotation now, and we're now going to attempt meridional circulation. My speculation to all the other helioseismologists here, I'm going to throw down my gauntlet, is this is probably the best method in helioseismology. We have to do some work in developing it, but it has probably the best signal to noise properties because we're using these global modes. And so we integrate across the entire mode line. And so we're not really throwing away any information. There's still some distance to go because we need to develop this method to try to do things like far side imaging and so on. It's not going to be that easy, but I think there's a great deal of merit in developing this technique. Okay, so here are the results. Srini again showed this. The horizontal axis is a harmonic wave number of this toroidal flow power. The vertical axis is velocity amplitude. And the black solid line is numerical simulations. So these are at different depths, and you can see this is deep, somewhat deep, this halfway down the convection zone, somewhat shallower, and this is at the surface. So the first thing that I want to show you is that there's this classical thing where power is increasing as a function of wave number. This is what we see in the sun all over the place. It's a very strong aspect of the convection measurements. And then the simulations do something very different. They peak at some intermediate low L, and then they sort of drop down. So the first thing, as I said, I want to show or want to draw your attention to is the fact that these two are simply different systems. So when we compare amplitudes between, let's say we say these are low convective, weak convective amplitudes. Well, it doesn't really it doesn't have much meaning because these curves are just simply different curves. So if I truncate it here and I say, what is the power between 0 and 20, then of course simulations are much larger than observations. But if I say, what is the power between 20 and 50, then the observations are going to be much higher than simulations. So it's really not a fair comparison. I mean, it's not a meaningful comparison. Not fair is not the right word. It's not a meaningful comparison to say that simulations and are overestimating amplitudes, but they're simply not estimating the right system. They're not exciting the modes the right way. They're not exciting, the distribution of amplitudes that you would think are the sun. And so that's one very important facet that I want. And this was even the case even with the 2012 result, although that was an upper bound, I guess. But then it's an important thing to realize that if the system looks that different, then simply looking at amplitudes is not a particularly useful measurement. So then the other thing that I want to say is the shape. So this is the power spectrum as a function that I told you, S minus mod P. It tells you a little bit about where power lies in the sun.
Sure.
Yeah.
You have 2 minutes more.
Only 2 minutes. Okay, then let me wrap it up. So it tells you a little bit about where the power lies. And so I want to show you, so I don't really need to explain the consequences in spectral space, but sorry, the results in spectral space. But the consequence in real space is that the power is localized to within plus minus 35 degrees. That's where the velocity power is sitting. Whereas numerical simulations are sort of broadband everywhere at all latitudes, horizontal axis is latitudes, and they sort of dip even in the close to the equator. So they are, yet again, it's the same thing that I was saying, they're looking at different systems, right? Here's equatorially confined power at the sun, equatorially depleted power in numerical simulations. And this sort of plot shows this as well. These are numerical simulations, and you can see all the power sitting at these low latitudes from HMI, but numerical simulations show dip in power in these low latitudes and so on. So that was another illustration of this result. So, so just 1 minute on the conclusions. As I said, solar convection is very close to the equator, a lot of power in the equator, but numerical simulations don't do this. And it's very important to look at to make meaningful comparisons, because if the system, if the numerical simulation is looking at something very different or predicting something very different, then simply comparing amplitudes is insufficient. You need a little more like a chisel, not just a sledgehammer. An amplitude is a sledgehammer, and this type of measurement could, moving towards the chisel. Okay, so there's a lot of work to be done in terms of trying to measure colloidal flows, and there's many important problems in this. I just want to say one thing, one last thing, which is that, it's still far from being proven, but Laurent's group, for instance, they've worked quite a bit on trying to understand Rossby waves and so on. And I think it's worthwhile to start expanding our search into what might be driving differential rotation of the sun, expanding our search into and limiting ourselves not just to convection as the principal mechanism, but looking at wave dissipation, which we know in atmospheric physics, in terrestrial atmospheric physics, plays a very important role in driving large-scale circulations. So on that note, I'd like to finish. Thanks very much.
Okay, thank you very much, Shravan, for the nice talk. And now we can take a few questions. Matthias?
Hello, Shravan. Thank you for the very nice talk, and it's really exciting that you now get also some information about the location of the power.
Mm-hmm.
The one thing I just wanted to mention, I mean, you talk in very general terms always about numerical simulations, but those simulations also come in a lot of different regimes, in particular in recent years. I mean, Nick Featherstone and Brad Hindman, they really looked into different regimes of rotational influence. And if I remember it correctly, they actually may have their simulations which have more these equatorial convection roles. So I think it might be worthwhile to look more into different simulation models, and actually maybe you can really use your observations to guide them which regime is likely the one which is closest to be realized on the sun.
Yeah, exactly right. You're exactly right, Matthias. In fact, they have these equatorial, they call it something, equatorially modulated convection and so on, which are, equatorially localized Taylor columns. And so you're exactly right. It really depends on the type of simulation, and it is important to therefore look at it. I apologize for using the term simulation poorly. It's been pointed out to me before, and I made the mistake again, but thank you for pointing this out.
Okay, so if there are any more questions? More questions could be posted on the Slack channel to the speaker. And speakers, please check the Slack channel later on. Thank you, Shravan.
Thanks a lot. Thanks a lot.
Now over to Rajguru.
Yeah, so thanks, Shravan. Our next speaker is Kiran Jain from the National Solar Observatory in Boulder. And Kiran is going to talk on far-side seismic mapping of the sun. Kiran, I will give you a warning at 15 minutes. You will have 20 minutes talk.
Okay, thank you, Rajguru. So, okay. So can you see my slide?
Yeah,
okay. Okay, so good evening for the participants in India and good morning who are joining from the United States. First, I must thank SOC for inviting me to give this presentation. And I'm going to talk about the far-side seismic mapping of the sun. The first question comes, why do we want to know about the far side when we cannot see? So left figure gives an explanation. When we look at the active regions, these are in the front side, which is shown by the lighter region, and on the far side, this is shown by the darker region. So you can see active regions are on the both sides. When sun rotates, regions from the far side come to the front, and they may produce a variety of storms. They can, and these storms may affect Earth's environment. So I have listed a few reasons why we want to study far side. The first and foremost reason is the tracking of solar activity. And because this is an important component in space weather prediction and studies. And we also want to study the global magnetic field that may play an important role in magnetic field models. And I feel if we have advance warning of the active region appearance on the front side, this may help us in planning for observation campaigns. So how do we measure activity on the far side? There are two methods. One is direct and other is indirect. Direct observations we can get from NASA stereo mission, and another is SWAN instrument on SOHO. Stereo was launched in 2006 with a hope to get continuous observations almost for a decade for the far side, but it didn't happen. In October 2014, one of the spacecraft of stereo stopped communicating, and now we are seeing only part of the far side from stereo. And in SWAN instrument, we get the we get Lyman alpha backscattered light, and we get some idea if there is a flare going on the backside, but we don't image the full backside. And in this image from SWAN, this is the latest. I cannot say latest. It was taken on 28th of February. So you can see the darker region is covered on the left. This is the far side, and on the right, this is the front side. And you can see the lighter region shown by blue are covered by the SWAN instrument, but darker regions, for darker regions, we don't have any observation. In direct method, we can use heliosmic mapping, where we use sound waves traveling within the sun can be exploited to map the far side. So I'm going to talk about the heliosmic mapping today in my talk. Let me start. Now I'm going to give you a brief history of heliosmic mapping. It was in 2000 when Charlie Lindsay and Doug Brown produced first seismic map of the far side using MDI, medium L observations. So in that, at that time, they had used the technique of acoustic holography that they had proposed in 1990, but it took almost 10 years to produce first seismic map of the front side, of the far side. So on the right, you see a picture from their science paper. There, they could map, they could identify active region 8194 on the far side, and this cross shows you the location of the active region near the far side central meridian. So it was identified here, and then on the next day again, sun has moved. So you can see this active region has moved a little bit more towards the east. And then what happened after 10 days, they could, there were direct observations where this active region was identified at the same location what they had proposed in their far side map. But in this paper, At that time, they had mapped only a limited region on the far side that was about 50 degrees from the disk center. Sooner after, they improved their technique, and now they were able to cover the entire sun using more escapes there. Here you can see on the left, there is a full disk of, I can say, there is a full sun map. So this is the front side, and that is the other is the back side. So in back side, now they were able to cover the entire sun. And you can see a small, this big circle at the center on the far side. This is the map they had produced using 2x2 escapes. I'm going to talk about this results obtained by acoustic holography in my talk. Most of the results are obtained by this technique. But I must mention, around same time distance technique was also used to map the far side, and it was done by Tom Duell and Sasha Kosovic. They had produced travel time variation maps, and this is the picture I got from their earliest paper in 2001. I'm sorry for the poor image quality here, because you cannot really see any signature of active region, but here I have marked by blue so that you can see, you can speculate like there was an active region here, and here what they could find in this region, the travel time was shorter by 6 seconds, and that they interpreted as the presence of active region. So what is the basic principle in seismic mapping? Here actually, I don't have to tell, like the sound speed increases with depth in the interior. So what happens when waves travel within the sun? It will be refracted back from the deeper layers to the surface. And then when this wave reaches to the surface, it will reflect back. So it keeps on going all the time. And we know sound speed below the active region is bit faster. So what happens when there is an active region in the path of the wave? When a wave comes back, it will come back little sooner. And this is the basic concept in far-sight imaging. So what we do, we calculate phase shift between the incoming and outgoing wave, and then use that as a measure of, as an indication of any region with high magnetic field on the far side. Once Charlie Lindsay and Doug Brown were able to establish their method, and they could show the presence of active region successfully in the far side, regular maps of far side were being produced using MDI data. And this is the map. As an example, I'm going to show you the map of active region 10486 that produced several that produced several severe storms during Halloween 2003. So here actually on the right, I have marked here. So there are two things you have to see. There are backside and the front side in the same map. So this line is the demarcation between front side and far side. So here, this is the portion, this is the portion of the far side. So this region was faintly identified here. And then as time progressed, you can see this region became stronger, and then it came to the front. So this was again successfully identified in far side mapping. But at that time, there was no calibration between the magnetic field or the active region area with the far side signature. It was later introduced by Irene Gonzalez Hernandez in 2007, where when she calibrated far side signal. This is phase shift given in radians with magnetic field and the region area. And you can see there is almost linear relationship between region area and the phase shift. But for the region with high magnetic field, it was linear, but magnetic field was not simple. It was not a linear relationship. It was a logarithmic relationship. And you can see this is the logarithmic scale on the x-axis for the correlation, for the calibration between magnetic field and phase shift. And later, after a few years, what she did, she combined these two calibrations to calculate the success rate of the appearance of regions identified on the backside. And on the basis of this, she found a way to compute probability. And we assign this probability to each active region identified on the far side to make sure if the probability is higher, we have higher chances of this region to come to the front. And this is the main measure right now to get the confidence in far side prediction. So here I show another example of the success of far side mapping using GONG. Now I am using GONG data. So this was during the evaluation of active region 12192 in 2014, October 2014, when there was a big active region was identified on the backside. And here actually, let me tell you, like this line, again, is between front side and the far side. And here is the far side and here is the front side. So this active region was identified on 7th of October, but it didn't come to the front until 17th. So in each map, in daily map, this region was consistent. And we were confident like it was going to come to the front, and it came to the front, and this you can see. So it was here. So this was another good example where we got confidence. Yes, we can. There is a reliable method where we can see the presence of active region on the far side. But does it stand true all the time? So to look at this, whatever we predict and whatever is there, there were several papers by Paulette Luer where she had compared far side maps with a composite AIA stereo 304 angstrom maps. So this is an example here I have shown, but let me tell you what she found in her work. It is really encouraging. 90% of the active regions that were identified in seismic maps were really present in the far side. But there were some false detection, and those false detection count about 10% of the predicted active region in the seismic maps. Another major point is she raised that we don't identify smaller active regions on the far side. And whatever regions we don't identify, there are many on the east limb. And here is an example of one big active region, that is 11429 in March 2012. It came to the front. So you can see 3 days maps for basically alternate day for a week in stereo. And you can see this active region was identified in a stereo map here and here. And then when it came to the front, it was really there. But what happened? When we looked at GONG far side map or HMI far side map, you don't see any signature of the presence of this active region. And this active region was not small, it was pretty big, and it produced two X class and several M class, and I don't know, maybe 60, 70 C class flares during its front disk passage. So you see, we were successfully identified some active region on the back, but we missed this. So it means our technique is not yet fully, I can say, foolproof.
Kiran, you have 2 minutes.
Wow. Okay, let me go quickly. So here actually, I'm going to compare results from acoustic holography with the time distance method, and Junwei Zhao recently did this work, and what he had done actually, he had compared far-side maps produced by time distance with the acoustic holography. And you can see there were some active regions, those were identified in time distance using more escapes, but these were not identified in acoustic holography maps. So there are, again, this is another indication, like there is a lot of work to be done in far-side mapping. So let me skip this part. Okay. So let me tell you what we did recently. We were able to predict the biggest active region of solar cycle 25 so far with our Heliosmic technique. So here, this was the active region 12786 that appeared on the front side on 23rd of November 2020. But we could see this active region almost 10 days in advance on the far side, and that we tracked, and then we made prediction on the 18th, 5 days before it came to the front. So we adopted 3 methods to get the confidence. One, we tracked the area of the active region throughout its far side passage and for several days, and we made sure like this active region was not depleting in size, means it was not going to decay. And when it came to the front, we could see like our active region area on the far side was in good agreement, but it grew fast in the front side and then started depleting. So let me show you how we tracked. So here you can see starting from November 13 to 22nd, it was on the far side. So we got some signature on November 13th, but it was at the noise level. But on 14th, we started getting some stronger signature. And then after November 14th, each day, this active region was present on the far side. And when I circle, it means there was a probability of 100%. So this was another criteria to get the confidence and just to make sure like this was going to come to the front. And in the right column, you can see this active region came to the front and it is marked by a red circle. So here actually what we do, we take 2 24-hour map and then average to get the, to improve the signal to noise. This result is, these maps were produced by Gong data and similar results were obtained by HMI. But you can see in Gong, we were able to identify this active region on November 15th, but in HMI, it was identified on November 16th. In their method, what they do, they take 5 maps of 24 hours and then do the averaging. Their signal to noise is much better than what we get in Gong, but they could identify this big active region a day later. So let me tell you what we can do with if we can use national NLST observations for far-side mapping. I will say these observations are not suitable for far-side mapping because of the single ground-based site. However, India has a node of Global Oscillation Network Group Gong at Udaipur, and we are using Udaipur's observation in far-side mapping on a regular basis. And here are the 6 sites of Gong, and here is in Udaipur. So India is also contributing to far side mapping, but we cannot use observations from NLST. And here I show the duty cycle, because we know we need higher duty cycle for far side mapping. The reason is sound wave takes almost 7 hours to make the full circle across the sun. So if our observations are shorter, then we are not going to get the reliable results. There will be more noise. So let me come to my last slide. So what we have seen till now, like we can reliably predict big active region, but there is less confidence when we go for a smaller active region. There are many hidden aspects that we need to explore. First is the detection of smaller active region, and other is the polarity assignment and tilt in active region. Some efforts were made by McDonald et al., but those were not fully successful, and they had put this I can say polarity assignment on the basis of Hale activity in their calculation, and then they recovered that. So that was not fully independent method. And another major development is on the reliable identification of active regions on the east limb. And another point that we want to lower the noise in far-side maps, that also introduces spurious identification of active regions. And I must tell, Max Planck group has done some theoretical work in this, but still there is a long way to go to get, I can say, when we are able to detect each and every active region on the far side maps. Thank you.
Thank you very much, Kiranji, for your nice talk on far side imaging, which can help in space weather predictions. So now it is open for questions. If there are any questions, please raise hands. Okay, so questions could also be posted on the Slack channel, and the speakers can check the Slack channel and answer the questions later on. Now over to Rajguru.
Okay, so thank you, Kiran. So our next speaker is Professor Alexander Kosovichov. Sasha is from the New Jersey Institute of Technology. And thank you, Sasha, for seeing you after a long time in this conference. So welcome to this conference. Sasha, you can go ahead with your presentation.
Hello, thank you. Can you hear me?
Yes, I can hear you.
Okay, good morning or good afternoon. Thanks me for giving opportunity to make presentation at this meeting. First, I'd like to congratulate the Institute, Indian Institute of Astrophysics, for half a century of remarkable discoveries and achievements. I've been at the Institute only once, more than 30 years ago. It was a symposium organized by Vinod Krishan and Eric Priest. And it was a really remarkable meeting. And I met many outstanding scientists. And in particular, I had opportunity to meet Kumar Chitri. And the heliosmology only started at the time, and I already have discussion how can we learn about physical properties, magnetism of solar interior from heliosmic observations. And then we met almost every year, first in Cambridge, and then every summer at Stanford. And last time when we met in 2019, we didn't meet last year, and he gave me his notes on 3 topics. And these topics are listed here. It's about inferences of meridian circulation pattern from measured rotational profile, convective instability growth rate in presence of rotation magnetic field, and also inference of turbulent kinetic energy from angular momentum balance in solar convection zone. You can see all his interest about mostly about inferences from what can learn from observations. And we actually started collaborating on this third topic, and unfortunately didn't finish this. And in particular, there was a lot of discussions about what can we learn about magnetic field. We cannot measure magnetic field directly by helioseismology, but what can we learn from helioseismic measurements? And in particular, that what also Douglas Goff was there and Antti participated in this work that we presented at Stanford. They actually deduce, from measurements of variations of angular velocity that we call torsion oscillations, they actually deduce distribution of Maxwell stresses in the interior. So first, let me remind you a bit about the solar cycle, what we know about the magnetic field. We measure on the surface, and here it's a butterfly diagram, and it's well known, and particular that one of the remarkable features of these observations is that the polar magnetic field measured at solar minimum predicts the strength of the next solar maximum. We don't quite understand why is this, and there are dynamo theories. And in particular, there are two paradigms in solar dynamo. And the flux transport theory, it's developed mostly in India with Arnab Chaudhuri and his school would develop a lot of that flux transport theory. And in this theory, the dynamo process mostly controlled by meridian circulation, particularly in the Tachak line. And this meridian circulation in the bottom convection zone explains the butterfly diagram. So it's quite sensitive to why there's a lot of interest in measuring meridian circulation at the bottom of the convection zone. And another theory, what suggested by Gene Parker in 1955, it's the dynamo theory. It's not sensitive to meridian circulation, it can work without meridian circulation. And it also explains the butterfly diagram. And one problem was that the butterfly diagram, the dynamo waves, they propagate along either rotation surfaces inside the sun. So when helioseismology discovered that these lines are almost radial or even go slightly up here, then there was a lot of skepticism about the theory because the dynamo wave would migrate to the polar regions. But then helioseismology discovered a subsurface rotational shear layer. And Axel Brandenburg first suggested that maybe this subsurface rotational shear is sufficient to turn the direction of the dynamo wave and it will travel towards the equator. So then with Valery Pipin, we did calculations model based on that mean field Parker's model and showed that indeed it's sufficient. If you allow toroidal field to penetrate into this layer, then it will turn the dynamo wave and create a butterfly diagram as we see on the surface. And this was confirmed also in a recent paper by Partgar, Chitri, and Krishan in 2019, that it also that they developed the dynamo theory in the subsurface shear layer. And there is one problem with this, and the problem is it's called extended solar cycle. This observation done by Dick Altrock at Zach Peak for many years. It's observations of coronal emission, and coronal emission showed that what we call extended solar cycle. These diagrams, butterfly diagrams, are extended not for 11 years, extended for more than 20 years, for 22 years, and they start from at the previous maximum, solar maximum, and that shows that there is what fast migration towards the pole called rush to the pole, and then a long migration that for 20 years towards the equator. And the same phenomenon was observed also in differential rotation and torsion oscillations. And it was a puzzle. We don't know how to explain this because magnetic field we see 11 cycles. And that the theory was first developed by Schuster and then Yoshimura. They showed they explained this by magnetic stresses, but that again that what only 11-year periodicity was explained. And then there was some ideas that because of why we see during solar minimum when there is no magnetic field on the surface. And Henk Spruit, I think he first suggested that it may be that some thermal effects. And he was kept asking to look, for decreasing of solar radiance in these places where we see torsion oscillations. And I look at this and that was too much noise to find this. I think Matthias Rempel suggested that the kind of double mechanism, that the thermal effects and magnetic effects combined to explain this phenomenon, extended solar cycle. So this is not exactly the direct relationship between flows and magnetic fields, and so not easy to understand. So then heliosmology can also measure torsional oscillations. Now we have two cycles from Gong and Soha SDO. They give similar results. And we also see in zonal subsurface flows, we also see torsional oscillations. And one puzzle was that we can see the cycle 23, but they disappeared in cycle 24. And then it turns out that we see this for cycle 24, but it's detected beneath the surface. That's what Rachel Howe first found this. And here, what I made this plot from a combination of MDI and HMI data that now it's they're posted at Stanford, all these observations. And indeed, we can see at the 0.9 solar radii, we can see that the branches, polar branch of this extended solar cycle. And the signal disappears. It's too much noise, and it's if you just look directly at velocity, that what signal becomes very weak. So what we need to do some analysis. Then remembering discussions with Kumar Chitri, I calculated acceleration instead of looking at the velocities it obtained by subtracting. It's not clear how to subtract mean velocity. So I calculated acceleration, and because it reflects directly the forces in solar interior. And then when overlay with magnetic field, it turns out that the zones of deceleration, they coincide exactly with location of magnetic field in both in polar regions and in the butterfly diagram where sunspots appear. So then was the idea that maybe that indeed, you know, what that zonal acceleration can reflect, can reveal that in the interior the dynamo waves. So what then I made this movie. It's a cross section of the zonal acceleration, and we can see, indeed, we can see some waves. We can see waves, traveling waves, and they remind the dynamo waves that we described by Parker. So there is some, they originate in some high latitudes, propagate quickly to polar regions, and at the same time there is a wave, slow wave that travels towards the equator. So that gives the idea that perhaps that indeed, you know, what we see, it's a dynamo waves in these variations of torsional oscillation in solar interior, and that the primary seat of solar dynamo is at base of convection zone at high latitude, 60 degrees latitude. So then, to make it more clear, but we had to do some analysis to filter in that what principal component analysis to filter out 11 components, basically, that what and 3 components, they describe pretty accurately these observations. There were some shorter term variations, and tachocline may be real, that what 2-year variations. But first we were focusing on 11-year variations. So that make it a bit clear, these diagrams, and also I did local correlation tracking of these waves. And this local correlation tracking shows that also that indeed, you know, what you can see, this kind of traveling waves originate in 2 branches. One originates, that both originate at the bottom of convection zone at 60 degrees latitude. And then one travels very quickly, one branch travels very quickly to the polar regions. And another takes about 10, 11 years travel towards the equator. So we can see in the interior, we can see both solar cycles. We can see here this in 2001, start of cycle 24. And also we can see that in progress is cycle 23 at the surface. So then we can track, of course, you know, through the whole convection zone, the signal, it becomes weaker and weaker with depth, but it still can be tracked. So this is time latitude diagrams at different depths that shows migration of these waves. And also we can make a plot, you know, tracking the diagrams at different latitudes with depths. And here indeed you can see that the bottom picture here shows that 60 degrees latitude, they travel very quickly. In 1 to 2 years, travel quickly to the surface. And at low latitudes here at like 15 degrees, it takes much longer and most slow down occurs in relatively shallow layers of this dynamo wave. And interesting that if you look, if you take these hypotheses, that we can see that the origin of the next solar cycle, that at the bottom of the convection zone, then for cycle 25, you already see the maximum. That was the most slows down, 60 degrees latitude at 0.76 solar radii. And we can see if we compare with the magnitude of the previous cycle, the magnitude is weaker. Of course, again, we can speculate that maybe that this cycle will be, in fact, much weaker than the previous cycle, but fortunately, we don't have much statistics at all the data here. And we don't know if this one-to-one correspondence to the sunspot number of these observations. It's still that. And we develop also, Valery Pipin developed a very detailed model. It took about 10 years of development of this mean field model. It takes into account, it's a fully dynamical model. It takes into account all physics that we know, all turbulent physics in mean field theory that we know. It takes into account the heat transport and all effects on heat transport of all flows, magnetic field, how that they affect the heat transport, and also the flows, differential rotation, meridian circulation, that also that all possible forces they can affect that, as we know, affect the differential rotation, meridian circulation, and also this classical mean field induction equation, also with all turbulent coefficients, anisotropies that caused by rotation and turbulent convection. So that it's a most complete dynamo theory, and it's fully dynamical. And it includes everything we know, and in fact, it predicts almost everything we see. So in particular, this model, it's not using differential rotation and meridian circulation as input. It predicts differential rotation and meridian circulation. In fact, it predicts then in very good agreement with observations, differential rotation. Meridian circulation, that it reproduces both one cell, double cell. In fact, if you take most recent solar model convection from MESA code, then the solution is a double cell, and the secondary cell is very weak. And it's if it's true, then that this cell unlikely to be absorbed by heliosmology because the secondary cell is very weak. But but the dynamo model is not much affected by this detail and meridian circulation. So what?
Shashar,
So yes.
you have 2 minutes.
Yes, yeah, I'll finish. Yeah. So also we look at the different driving forces of in this model, calculate all different driving forces to understand the origin of torsion oscillations. And in fact, so this model reproduces the extended solar cycle. Here, this particular, what on this plot showed that acceleration, that it's kind of the change amplitude is changes with during solar cycle of zonal flow, but it does reproduce torsion oscillations, extended solar cycle. It turns out that this analysis showed that it's very interesting that not direct of magnetic forces. The physics is it's more complicated. It turns out that magnetic field quenches the heat transport, and this affects, this modulates meridian circulation, and modulation of meridian circulation causes the variations of torsion oscillations. So this was explanation of the torsion oscillation. So at the end, I showed just movies, how in this model you can see this propagation of this toroidal magnetic field. And you can see how it new magnetic field appears at high latitudes at the bottom convection zone, and then waves travels. So at one branch travels very quickly to the polar region. That explains why the polar magnetic field predicts the next solar cycle. And also there is a slow wave. It travels to the equator. So here it's a coronal field, how the solar corona evolves in this model, and with solar cycles. So we can see this also reproduces the structure of the solar corona. So that what one was interesting predictions was that the model predicted extended solar cycle of meridional circulation. So it explained this convergent flows of meridional circulation towards active latitudes, but also predicted that the extended structures of these flows, so that you can see these variations of meridional circulation even during solar minimum, where there's no magnetic field, no active regions. And we did recently analysis with Gatling and Jean, and analysis of HMI data using time-distant heliosismology, and also Rudy Combe did using ring diagrams. And indeed, we can see, particularly this plot, we can see these variations of meridional circulation during solar minimum, so that indeed there is an extended solar cycle of the meridional circulation. So that's the main results that by tracking migration of these torsion oscillations, trim jets in solar interior, virial patterns of dynamo waves that control sunspot cycles, and heliosmology measurements, they allow us to pin down location of solar cycle originates. It's in tachocline, 60 degrees latitude. And the dynamo model is self-consistent, fully nonlinear mean field dynamo model explained the extended solar cycle phenomenon. And also this heliosismology data shows that something fundamental changes happened inside the sun. Perhaps the next solar cycle may be even weaker than current cycle. Thank you.
Thank you very much, Sasha, for your nice talk on the torsional oscillations and also highlighting your memoir with Professor Chitre. So now the talk is open for questions. Divyendu, I can see your raised hand.
Yeah, Sasha, so it appears to me that you're interpreting your observations based on dynamo waves, which is like alluding to the mean field alpha omega dynamo proposal of Parker. However, all you are seeing really is signatures of toroidal field migration and probably their feedback on the flows. This cannot distinguish between mean field dynamos and Baphomet flux transport dynamos. In particular, the interpretation that this is a mean field dynamo wave flies in the face of many observational constraints, theory, and data-driven modeling that conclusively demonstrates that the variations that you see in the tilt angle and flux of emerged active regions completely explains the variability in the polar field strength at the minimum of a cycle, and hence the next transport cycle amplitude. So it seems to me that you are sort of ignoring this vast literature and observational constraints that's there. Would you like to comment on that?
No, we don't ignore anything. In fact, this model includes the flux transport. It includes everything like the flux transport model. And but as I said, it doesn't impose meridional circulation. It also reproduces meridional circulation. And in terms of interpretation, how we can actually distinguish between these two models, I think, there's no such separation in these models, that in fact, the dynamo model includes both the flux transport and also dynamo waves. We cannot exclude dynamo waves. It's a diffusion process.
I agree with.
So that and our model includes, both of these processes. We don't, I didn't say that we rule out the flux transport model.
Okay, so if you're saying that both works together and it's just that we're interpreting the toroidal field migration, I'm absolutely fine with that. So I think we have some convergence there.
Yeah, but what's most important is not just to solve induction equation, but also to look, what you said back reaction.
Mm-hmm.
So it must be fully consistent, then you get, more understanding of the dynamics.
Okay.
Rajguru, I can see raised hand.
Yeah, Sasha, very presentation, Sasha. So I was just wondering, I saw your animation for the dynamo wave, one for the poleward propagating and the other one for equator propagating. So is there the prediction for the meridional flow? Is it what kind of structure it has? Is there a double cell structure in the latitude or?
No double cell structure in latitude in this model, and this model predicts that what also was a paper by Hota that what they also showed that what the origin how we can get in these models in the secondary cell, And it turns out if you include in this theory, in field dynamo theory, if you include variations of turbulent, turbulent convective time with radius, then the secondary cell appears. But it's in radius, not in latitude. And latitude in this theory, it didn't appear the secondary cell.
Okay, all right.
Question is from Arnav. Arnav, please go ahead.
Yeah. So Sasha, I wanted to ask you for some clarification about your claim that in your mean field model, you do not put the differential rotation and meridional circulation, but they come out of the theory. And of course, we know that there are some mean field theories of differential rotation and meridional circulation based on something like lambda effect, which Rudiger and Kichatinov developed, but that's something a very complicated subject. So can you clarify a little bit more? What do you mean by this thing that these large scale flows come out of your mean field model?
Yeah, this model, in fact, it includes lambda effect, of course. Without lambda effect, we cannot explain in mean field theory the differential rotation. So it's kind of a combination of what we have. This theory was developed by Kichatinov originally. So it's a combination of this Kichatinov theory of differential rotation within circulation with the mean field magnetic dynamo model, with the model that includes into account also magnetic effects that's the classical induction equation, which we studied in detail. So it's a combination of these two. Did it answer your question, Arnab?
Yeah, thank you. And one other point which Dibbendu already made, that from this observation, it's difficult to distinguish between dynamo wave model and the flux transport dynamo model. So I may mention that many of these observations were explained on the basis of a flux transport dynamo model in a paper which I published in Physical Review Letters in 2009 with Chakravarti and Chatterjee, Chakravarti, Chaudhuri and Chatterjee. So certainly, I think there have been attempts of explaining these observations with the flux transport dynamo model, and there have been reasonable success. I don't know whether our model is correct or not, but I would say that there has been reasonable success.
Yeah, here that again, that what I'm not in favor of separating of these, because I think that both effects they play a role in dynamo. And what is what I don't like about flux transport model, what is it's a kind of truncated interpretation of these, in particular interpretation that the butterfly diagram is explained by migration of magnetic flux in the bottom convection zone and emergence of that we know that you need a very strong magnetic field to emerge at low latitudes, otherwise Coriolis force will move to the high latitudes. And so that a lot of contradictions also with observations in terms of rotation of magnetic flux. It doesn't rotate with the speed of tachocline. There are some disconnections, and then it's difficult to explain that what we call active longitudes. So that but both processes, they definitely play roles. That what the flux transport, and so flux transport is transport by flows, and dynamo waves, it's a diffusion, essentially, right? Magnetic diffusion.
Sasha, let me just comment here that Matthias Rempel did a work. I don't remember the year. It was in APJ, where he showed that even when you consider nonlinear Lorentz feedback of magnetic fields on the meridional flow, even then, flux transport by meridional flow towards the equator is possible in dynamical models as well. So that criticism doesn't apply. I'm not saying that means meridional circulation is the only means of transporting, but that has been looked at, and it looks like it does work, even in dynamical models.
Well, maybe that it works, but what again, my point is that if you want to understand, what's happening inside the sun, And it's again that what I follow that what the discussions with Kumar Chitri, you have to take into account, the exact physics, what you cannot
Oh,
just
sure.
take,
I mean, nobody's
some
disputing
particular,
that.
some extract, something that what if you do what Valery Pipin did, then you can see that where the flux transport works, where the dynamo wave works, and it's very clear. We can see dynamo wave, what if you can explain with any other theory, what we see in variations of differential rotation, torsion oscillations, and also meridian circulation now that because you see variations.
But a major challenge there has been producing.
If any other theory can explain this, but I believe, what currently what is the difference now, what the difficulties that we have now, that what I think the next step is to understand actually this turbulence. We use mean field turbulence. It's separation of scales. And now what currently we put in some effort to understand this lambda effect and alpha effect from 3D simulations. Now with a bit disconnection between simulations and this turbulence. I think, I don't like, this discussions that what the flux transport versus dynamo waves, that I think they both work together. And
okay, there is a question by Rob. I can see in the chat box. Rob, are you around? Rob? So Rob is asking, seems to explain active latitudes well. What about active longitudes? Activityness. Yeah, okay.
Well, active longitude, we did some first steps to explaining this, that you need to include non-axisymmetric modes. This in principle, this model is it's three-dimensional. It turns out that there was and in dynamo that that people who work in dynamo theory, they know that the dynamo instability it's mostly for axisymmetric modes. Non-axisymmetric modes, these modes are even stable, so they're linked for some sort of non-linear effects. So it's already that what did some studies on this, extending this model to non-axisymmetric, and there is some encouraging results. I didn't have time to present here. So this model that what we just need to add some non-axisymmetric harmonics and see how it couples to primary dynamo instability, which is axisymmetrical in fact.
Okay, thank you, Sasa, very much. And if there are more questions, please post it on the Slack channel. And now over to Rajguru for concluding the session.
Okay, so thank you, Sasha. It was
thank you.
Interesting presentation, and thanks for joining in this meeting. Yeah, so we had a very long day here today. I think we will call it a day, and we will meet tomorrow at 8:30 Indian time. There's the first session in the morning is on dynamos again, and let's meet tomorrow. Thank you, everyone, and have a good morning in US and other people. I think in India, we are too tired now. We go back and sleep. So see you all tomorrow.